Hello, trigonometry. These are the video notes for lesson 17, Law of Sines. So our law of sines is basically a proportion relating the sine ratio of an angle to the opposite side of that angle. So the first thing we want to do is label this triangle and just make sure we understand that capital letters represent angles and that lowercase letters represent sides and that a side is always across from its corresponding angle. So if this is A, this is B, this is C, then little b is the side on the left, and little c is the side on the right. And it's very intentional to have these capital letters represent sides and the lowercase letters, capital letters represent angles and the lowercase letters represent sides. So when I'm using the sine rule, we only use two at a time. So we'll either use A and B, B and C, or A and C. We won't tend to set up equations with all three. And feel free to reciprocate these. So you can have side over angle ratio, or you can have sine ratio over side. And it would work both ways. So let's take our same example, and you can see the lettering notation is a little bit different here. But let's talk about why the law of sines works. All the trigonometry we've done so far has been based on right triangles and the unit circle. So what we're trying to do is extend our knowledge of right triangle trigonometry, your SOHCAHTOA ratios, and apply them to a non-right triangle. So imagine taking ABC and splitting it with this mystery side length x, and this 90-degree angle here, which makes this an altitude. So if we're looking for a ratio, we can identify that sine A is equal to x over the hypotenuse of this right triangle, which as you can see is across from angle B, which makes it side little b. On the other side, we have angle B, use two swoops, and we get sine B is equal to x over this right triangle's hypotenuse, which is across from angle A, and you can see is little a. Well, both of these equations are defined in terms of x. So let's solve them each for x. Over here, we can multiply both sides by b equals x. And on this one, we can multiply both sides by a. And since they're both equal to x, that means these equations can be set equal to each other using the substitution method for solving. B sine A equals A sine B. And then we're going to divide each side by AB. And watch what happens. These A's cancel, these B's cancel, and we're left with sine A over A is equal to sine B over B. So this is essentially the origin of the law of sines and cosines. And technically, if you wanted to, you could solve non-right triangles by breaking them down into right triangles and solving that way. It's just a little bit more time consuming. So the law of sines is really a shortcut for solving non-right triangles. Now we're going to get into two examples before we talk about something called the ambiguous case. So for this first example, you can see that we have this angle right here and the side across from it. We have this angle right here, and that's about it. So let's label this side A, and let's label this side B. And then we know that the angles in a triangle have to add up to 180, so we can add 30 and 111 to get 141, and subtract 141 from 180 to get 39 degrees for angle B. Because there weren't any directions on this problem, it's just an example, right? I'm just going to solve the whole thing. And that means finding all sides and all angles. Now I can set up my first ratio. Let's solve for side A. Whenever I'm writing an equation, I always modify the law of sines so that the goal, the variable I'm solving for, is in the top left corner of the proportion. So it's side over sine ratio equals side, which the only other side we have in this problem is 43, over sine ratio. And by making sure that I always put my objective variable in the top left, I know that my second step will always be multiplication. So in this case, I want to multiply both equations by sine 30 degrees. And I'm going to cancel that. I think sine 30 is just 1/2, which is interesting because this is not a right triangle, but those ratios still hold true. Typing this into your calculator, make sure that you are in degree mode, not radians, because that is going to affect your answer. These are measured in degrees. We get the first side answer as 23.02, which we're going to round to 23. I prefer my side lengths to be measured to the nearest tenth and my angles to be measured to the nearest whole number. Now let's repeat this process for side B. Side B over the sine ratio of the opposite side, which is 39 degrees, equals, and again, we're going to go back to the given. Remember that the 23 is rounded, so we don't want to use this rounded value to solve further problems if we can avoid it. I'd rather go back to using 43 and sine 111. With that, multiply both sides by the sine of 39, and we'll have a value for side length C and be done solving this triangle. Keep in mind, when you have two angles, you can quickly and easily use the 180 rule. The angles in a triangle add up to 180 to find the third angle. But you cannot use Pythagorean theorem if you know two sides because you don't have a right angle. So I typed this problem into my calculator and I got 28.986. Rounding that to the nearest tenth, I'm actually going to round up to 29.0. Let's take a look at our second example. This one actually looks like it might be a right angle. Maybe this is like 91 degrees. But you can see in this problem, we don't have two angles to start with. We're going to actually have to find one of these missing angles. So if we look, the 58 degrees is across from the 28. And the 16 is across from B. So I'm going to make angle B my first goal and put it in the top left. So now it's going to be sine ratio over the opposite side equals sine ratio over the opposite side. Now you don't have to set these proportions up so that your variable is in the top left corner. That's just my preference and my recommendation. If you put it somewhere else, just make sure you're following proper algebraic techniques like cross multiplication to get the variable by itself. Switch colors, multiply both sides by 16, and we get sine B is equal to whatever that is. All right, so we're getting some crazy decimal, 0.48459, which we're going to round up to 46. And so what you end up here is a trigonometric equation. We're trying to solve for angle B, and we need inverse trig to solve for angles. So the best way to do this is to not round this answer and leave it in your calculator, and then use your ANS or answer feature in your calculator, that storage that it has, to plug it in. Since we're rounding to the nearest whole number, it should be okay if you end up rounding. You should be able to get B is equal to 29 degrees either way, but just some advice is to use the ANS feature. So if B is 29 degrees, we can use our 180 knowledge to subtract from 180. So we'll do 29 plus 58 and subtract that from 180. And that gives us 93 degrees. This really was almost a right triangle. But because angle A is not exactly 90 degrees, we can't use the Pythagorean theorem to find this missing side. We need to set up one more sine ratio. I'm going to refer back to the first ratio we used in the last problem. This didn't have any rounding, right? This was given to us. So this is the preferred ratio to use to solve all problems. Since now I'm solving for side A, I'm going to put A in the top left corner. And it's side over sine ratio. And then side, 28, over sine ratio. Multiply both sides by sine 93, and go ahead and type this into your calculator. So I'm getting 32.97, and if I actually round that to the nearest tenth, I'm just going to get 33. So there are my three answers. Side A is 33, angle B is 29, and angle A is 93 degrees. This is going to conclude part 1 of the video notes. In the next part, we're going to talk about the ambiguous case for the law of sines.